Hello, and welcome back to our astronomy course. Okay, so today we will be continuing study our nearest star, namely called the Sun. But uh, nothing more. Let's start this topic. So, so bubbles, stars are structures balanced between opposing forces that individually destroy them. The sun is a ball of hot gas held it together by its own gravity. If it were not for the sun's gravity, the hot, high pressure gas in the sun's interior would explode outward. Likewise, if the sun were not so hot, its gravity, in this case, would compress it into a small, dense body. And in this section of our lecture, you will discover how the sun generates its heat. Okay? One second. And the sun is powered by nuclear reactions that occur near its center. The energy keeps the interior hot and keeps the gas totally ionized. I hope you remember what means ionized gas. It's a loss of an extra electron. And that is, the electrons are not attached to atomic nucleus. So the gas is an atomic soup of rapidly moving particles colliding with each other at high velocity. Nuclear reaction inside stars involve atomic nuclei, not whole atoms. How exactly can the nucleus of the atom yield energy? The answer lies in the forces that hold the nuclei together. The sun generates its energy by reconnecting the bond between the particles inside atomic nuclei. This is quite different from the way you would generate energy by burning wood in a fireplace. The process of burning wood extracts energy by breaking and rearranging chemical bonds among atoms in the wood. Are you agree with me? Nice. Chemical bonds are formed by the electrons in atoms, and you saw in the chemistry that the electrons are bound to the atoms by the electromagnetic force. So, the chemical energy released when these bonds and broken and rearranging originate in the electromagnetic force. There are only four forces in nature: the force of gravity, the electromagnetic force, the weak force, and the strong force. The weak force is involved in the radioactive decay of certain kinds of nuclear particles, and the strong force bind together atomic nuclei. Nuclear energy comes from the strong force. Nuclear power plants on Earth generate energy through nuclear fission reactions that split uranium nuclei into less massive fragments. A uranium nucleus contains a total of 235 protons and neutrons. And when it decays, it splits into the range of fragments containing roughly half as many particles. Because the fragments produced are more tightly bound than the uranium nuclei, the binding energy is released during uranium fission. Stars don't use nuclear fission. They make energy in nuclear fusion reactions that combine light nuclei into heavier nuclei. The most common reaction, the one that occurs in the sun, fuses hydrogen nuclei, or single proton, into helium nuclei, which contain 2 protons and 2 neutrons. Because the nuclei produced are more tightly bound than the original nuclei, energy is released. And this figure shows how tightly different atomic nuclei are bound. The lower in the diagram, the more tightly the particles in a nucleus are held. Notice that both fusion and fission reactions move downward in the diagram toward more tightly bound nuclei. They both produce energy by releasing the binding energy of atomic nuclei. When 4 hydrogen nuclei fuse to make 1 helium nucleus, a small amount of matter seems to disappear. And you can see in this expression here. When we have 4 hydrogen nuclei proportional 6.69 times in 10 in power minus 27 kilos, and minus 1 helium nucleus 6.64 times in 10 in power minus 27 kilos, we have the difference in mass in this case. It's very, very small, 0.048 times 10 in power minus 27 kilos. So that mass is converted to energy according to Einstein's equation. And we have this expression. The famous Einstein equation, E proportionals mc squared. And we put our units and we can this. 0.048 times 10 power 27 is the mass and the speed of light, 3 in 10 power in 8 meters per second. And this must be squared, right? As a result, we have this quantity of energy, 0.23 times 10 in power minus 11 joule. Recall that the 1 joule is roughly equal to the energy of an apple falling from a table to the floor. And the sun fuses together 4 hydrogen nuclei to make 1 helium nucleus. Because 1 helium nucleus has 0.7% less mass than 4 hydrogen nuclei. And it seems that some mass vanish into the process. In fact, that mass is converted to energy. And you could figure out how much by using Einstein's famous equation E proportional mc squared. You can symbolize the fusion reactions in the sun with a simple nuclear reaction. And this is the right side of this slide. 4 hydrogen, transformed into the helium with 4 mass and n plus energy. So more detail, in this equation, H and 1 represent a proton, okay? And the nucleus of the hydrogen atom and the 4 helium on this side represent the nucleus of a helium atom, okay? And the superscripts indicate the approximate weight of the nucleus. It means the number of protons plus the number of neutrons. Okay, nice. The actual steps in the process are more complicated than these convenient summaries suggest. Instead of waiting for 4 hydrogen nuclei to collide simultaneously, a highly unlikely event, the process can proceed step by step in a chain of reaction, the proton-proton chain. The proton-proton chain is a series of three nuclear reactions that builds a helium nucleus by adding together protons. And this process is efficient at temperatures above 10,000 Kelvin. The sun, for example, manufactures over 90% of its energy, namely in this way. The three steps of the proton-proton chain entail these reactions, and you can see in the bottom of the slide. In the first reaction, the two hydrogen nuclei, two protons, combine to form a heavy hydrogen nucleus called deuterium, emitting a particle called a positron E+, a positively charged electron, and a neutrino nu E, a subatomic particle having an extremely low mass and a velocity near equal to the velocity of light. In the second reaction, the heavy hydrogen nucleus absorbs another proton, and with emission of a gamma ray, gamma, becomes a lightweight helium nucleus. And finally, two lightweight helium nuclei combine to form a common helium nucleus and two hydrogen nuclei. Nice? Okay. Because the last reaction needs two light helium nuclei, the first and second reaction must occur twice. And the net result on these chain reactions is the transformation of four hydrogen nuclei into one helium nucleus plus energy. The energy appears in the form of gamma rays, positrons, and energy of motion of particles and neutrinos. The gamma rays are photons that are absorbed by the surrounding gas before they can travel more than a fraction of a millimeter. This heats the gas. The positrons produced in the first reaction combined with free electrons, and both particles vanish, converting their mass into gamma rays, which are absorbed and also help keep the gas hot. In addition, when fusion produces new nuclei, they fly apart at high velocity and collide with other particles. This energy of motion helps rise the temperature of the gas. The neutrinos, on the other hand, don't heat the gas. Neutrinos resemble photons, except they almost never interact with other particles. The average neutrino could pass unhindered through a lead ball of light year thick. Consequently, the neutrinos do not warm the gas, but race out of the sun at nearly the speed of light, carrying away roughly 2% of the energy produced. Creating one helium nucleus makes only a small amount of energy, hardly enough to rise a house flying 1,000th of an inch. Because one reaction produces such a small amount of energy, it is obvious that many reactions are necessary to supply the energy needs of a star. The sun, for example, needs to complete 1,038 reactions per second, transforming 5 million tons of mass into energy every second. It might sound as if the sun is losing mass at a furious rate, but in its entire 10 billion years lifetime, the sun will convert less than 0.07% of its mass into energy. How funny. It is a common misconception that nuclear fusion in the sun is tremendously powerful. After all, the fusion of a milligram of hydrogen, it means roughly the mass of a match head, produces as much energy as burning 30 gallons of gasoline. However, at any one time, only a tiny fraction of the hydrogen atom is fusing into helium, and the nuclear reactions in the sun are spread through a large volume in its core. Any single gram of matter produces only a little energy. A person of normal mass eating a normal diet produces about 4,000 times more heat per gram than the matter in the core of the sun. How funny comparison this? And the sun produces a lot of energy because it contains a lot of grams of matter in its core. I agree with you. But fusion reactions can occur only when the nuclei of two atoms get very close to each other. Because atomic nuclei carry positive charges, they repel each other with an electrostatic force called the Coulomb force. Physicists commonly refer to this repulsion between nuclei as the Coulomb barrier. To overcome this barrier, to get close together, atomic nuclei must collide violently. Violent collisions are rare unless the gas is very hot, in which case the nuclei move at high speed and collide violently. Remember, an object's temperature is related to the speed with which its particles move. So, nuclear reaction in the sun take place only near the center, where the gas is hot and dense. A high temperature ensures that a few of the collisions between nuclei are violent enough to overcome the Coulomb barrier. And the high density ensures that there are enough collisions and thus enough reactions to meet the sun's energy needs. Now you are ready to follow the energy from the core of the sun to the surface. The surface is cool, only about 5,800 Kelvin, and the center is over 10 million Kelvin. So energy must flow outward from the core, right? Yeah. Because the core is so hot, the photons bouncing around there are gamma ray. Each time a gamma ray encounters an electron, it is deflected or scattered in a random direction. And as it bounces around, it slowly drifts outward toward the surface. That carries energy outward in the form of radiation. So astronomers refer to the inner part of the sun as a radiative zone. To examine this process, imagine picking a simple gamma ray and following it to the surface. As your gamma ray is scattered over and over by the hot gas, it drifts outward into cooler layer, where the cooler gas tends to emit photons of longer wavelength. Your gamma ray will eventually be absorbed by the gas and re-emitted as 2 X-rays. Now you must follow those 2 X-rays. They bounce around, and soon you will see them drifting outward into the even cooler gas, where they will become a number of longer wavelength photons. The packet of energy that began as a single gamma ray gets broken down into a large number of lower energy photons. And it eventually emerges from the sun's surface as about 1,800 photons of visible light. But something else happens along the way. The packet of energy that you began following in the core eventually reaches the outer layer of the sun, where the gas is so cool that it is not very transparent to radiation. There, energy backs up like water behind a dam, and the gas begins to churn in the convection. Hot blobs of gas rise, and cool blobs sink. In this region, now as a convective zone, the energy is carried outward as circulating gas. The radiative and convective zones are shown in this figure. The granulation visible on the photosphere is clear evidence of a convective zone just below the photosphere, carrying energy upward of the surface. Sunlight is nuclear energy produced in the core of the sun. The energy of a single gamma ray can take 1,000,000 years to work its way outward, first as a radiation and then as a convection of its journey to the photosphere. It is time to ask the critical question that lies at the heart of science. What is the evidence to support this theoretical explanation of how the sun makes its energy? Nuclear reactions in the sun's core produce floods of neutrinos that rush out of the sun and off into space. Over 1,012 solar neutrinos flow through your body every second. Nice. But you never feel them because they are almost perfectly transparent to neutrinos. If you could detect these neutrinos, you could probe the sun's interior. You can't focus neutrinos with a lens or mirror, and they zip right through detectors used to count other atomic particles. But neutrinos of certain energies can trigger the radioactive decay of certain atoms. That gives astronomers a way to count solar neutrinos. In the 1960s, chemist Raymond Davids devised a way to count neutrinos produced by hydrogen fusion in the sun. He buried a 100,000-gallon tank of cleaning fluid, usually it's a perchlorate ethylene, C2C14, in the bottom of a South Dakota gold mine, where cosmic rays could not reach it. Let's look at this slide, especially on the left part. And counting the number of times a neutrino triggered a chlorine atom into becoming an argon atom. He expected to detect the neutrino a day, but he actually counted 1/3 as many as expected, only one every 3 days. The Davis neutrino experiment created a huge controversy. Were scientists wrong about nuclear fusion in the sun? Did they misunderstand how neutrinos behave? Because astronomers had great confidence in their understanding of the solar interior, and they didn't abandon their theories immediately. It took over 30 years, but eventually physicists were able to build better detectors. And they discovered that neutrinos oscillate among 3 different types, which physicists call flavors. Let's look at the right part of this slide. Nuclear reactions in the sun produce only one flavor, and the Davis experiment was designed to detect or taste that flame. But in the 8-minute journey from the sun's core to Earth, the neutrinos oscillated so much they were eventually distributed among the 3 different places when they arrived at Earth. That's why the Davis experiment detected only 1/3 of the number predicted. In 2007, scientists announced that a super-sensitive experiment in a tunnel under the Italian Alps had detected 50 neutrinos a day coming from the sun. The neutrinos have lower energies than those caught by the Davis experiment and are produced by a side reaction that produces beryllium-7. The number of neutrinos detected matches the prediction of models of nuclear fusion in the sun. The center of the sun seems forever beyond human experience. But counting solar neutrinos provides the evidence to confirm the theory. The sun makes its energy through nuclear fusion. Why does nuclear fusion require that the gas be very hot? This argument has to include the basic physics of atoms and thermal energy. Inside a star, the gas is so hot it is ionized, which means the electrons have been stripped of the atom's leaving pair, positively charged nucleus. In the case of a hydrogen, the nuclei are single protons only. These atomic nuclei repel each other because of their positive charges. So they must collide with each other at high velocity if they are to overcome that repulsion and get close enough together to fuse. If the atoms in a gas are moving rapidly, then the gas must have a high temperature. So nuclear fusion requires that the gas be very hot. If the gas is cooler than about 10 million Kelvin, hydrogen can't fuse because the protons don't collide violently to overcome the repulsion of their positive charges. It is easy to see why nuclear fusion in the sun requires high temperature. But now expand your argument. Why does it require high density? The sun is unquiet. It is home to slowly changing spots larger than Earth and vast eruptions that dwarf human imagination. All of these seemingly different forms of solar activity have one thing in common: magnetic field. The weather on the sun is magnetic. Solar activity is often visible with even a small telescope, but you should be very careful if you try to observe the sun. Sunlight is intense, and when it enters your eye, it is absorbed and converted into thermal energy. So be careful. The infrared radiation in sunlight is especially dangerous because your eyes can't detect it. You don't sense how intense the infrared is, but it is converted to the thermal energy in your eye and can burn and scar your retina. It is not safe to look directly at the sun, believe me. And it is even more dangerous to look at the sun through any optical instrument, such as a telescope, binoculars, or even the viewfinder of a camera. The light gathering power of such an optical system concentrates the sunlight and can cause severe injury. So, never look at the sun with any optical instrument, okay? Unless you are certain it is safe. And this slide shows a safe way to observe the sun with a small telescope. In the early 7th century, Galileo observed the sun and saw spots on its surface. Day by day, he saw the spots moving across the sun disk. He rightly concluded that the sun was a sphere and was rotating. If you repeated his observation, you would probably see something that looks like in figure B on the center of this slide. And you would see sunspots. The dark sunspots that you see at visible wavelengths only hint at the complex process that go on in the sun's atmosphere. To explore those processes, you must analyze images and spectra at a wide range of wavelengths. Study sunspots and the sunspot cycle, and notice 5 important points and 4 new terms. First, sunspots are cool spots on the sun's surface caused by strong magnetic field. Second, sunspots follow an 11-year cycle, becoming more numerous, reaching a maximum, and then becoming much less numerous. The Monte butterfly diagram shows how the location of sunspots changing during a cycle. 3. The Zeeman effect gives astronomers a way to measure the strength of magnetic field on the sun and provide evidence that sunspots contain strong magnetic field. 4. The intensity of the sunspot cycle can vary from cycle to cycle and appears to have almost faded away during the Maunder minimum in the late 17th century. This seems to have affected Earth's climate. And 5, the evidence is clear that sunspots are part of active regions dominated by magnetic fields that involve all layers of the sun's atmosphere. The sunspot groups are merely the visible traces of magnetically active regions. But what causes this magnetic activity? The answer is linked to the waxing and waning of the sun's overall magnetic field. The sun's magnetic field is powered by energy flowing outward through the moving current of gas. The gas is highly ionized, so it is a very good conductor of electricity. When an electrical conductor rotates rapidly and is stripped by convection, it can convert some of the energy flowing outward as converting into a magnetic field. This process is called the dynamo effect, and it is believed to operate in Earth's core and produce Earth's magnetic field. Helioseismologists have found evidence that the dynamo effect generates the sun's magnetic field at the bottom of the convective zone deep under the photosphere. The sun's magnetic field cannot be as stable as Earth's. The sun does not rotate as a rigid body. It is a gas from its outermost layers down to its center. So some parts of the sun can rotate faster than other parts. The equatorial region of the photosphere rotates faster than the region at high latitude. As you can see on the left figure, at the left part of this slide. At the equator, the photosphere rotates only every 25 days, but at latitude, for example, 45 degrees, one rotation takes 27.8 days. Helioseismology can map the rotation through the interior, as you can see on the right side of this slide. And even the different levels rotate with different periods. This phenomenon is called differential rotation, and it is clearly linked with the magnetic cycle. Also, the magnetic cycle is not fully understood. The Babcock model, named for its inventor, explains the magnetic cycle as a progressive tangling of the solar magnetic field. Because the electrons in an ionized gas are free to move. The gas is a very good conductor of electricity. So any magnetic field in the gas is frozen into it. If the gas moves, the magnetic field must move with it, right? And the sun's magnetic field is frozen into its gases. And differential rotation wraps this field around the sun like a long string caught on a cupcake. Rising and sinking gas currents twist the field into rope-like tubes, which tends to float upward. The model predicts that sunspot pairs occur where these magnetic tubes burst through the sun's surface, as you can see in this slide. Sunspots tend to occur in groups or pairs, and the magnetic field around the pair resembles that around a bar magnet, with one end magnetic north and the other the magnetic south, just as you would expect if a magnetic tube emerged through one sunspot in a pair and then re-entered through the other. At any one time, sunspot pairs source and the sun's equator have a reverse polarity compared with those the north and the sun's equator. The figure in this slide, which you can see now, illustrates these by showing sunspot pairs south of the sun's equator, with magnetic south poles leading and sunspot north to the sun's equator, with magnetic north poles leading. At the end of 11 sunspot cycles, the new spots appear with reverse magnetic polarity. The Babcock model explains the reversal of the sun's magnetic field from cycle to cycle. As the magnetic field becomes tangled, adjacent regions of the sun are dominated by magnetic fields that point in different directions. After about 11 years of tangling, the field becomes so complex that adjacent regions of the sun begin changing their magnetic field to agree with neighboring regions. The entire field quickly rearranges itself into a simpler pattern, and differential rotation begins winding it up to start a new cycle. But the newly organized field is reversed, and the next sunspot cycle begins with magnetic north replaced by magnetic south. Change. Consequently, the complete magnetic cycle is 22 years long, and the sunspot cycle is 11 years long. Okay? This magnetic cycle explains the Maunder butterfly diagram. As the sunspot cycle begins, the twisted tubes of magnetic force first begin to float upward and produce sunspot pairs at higher latitude. Consequently, the first sunspots in a cycle appear farther north and south of the equator. Later in the cycle, when the field is more tightly bound, the tubes of magnetic force arch up through the surface closer to the equator. As a result, the later sunspot pairs in a cycle appear closer to equator. Notice the power of a scientific model The Babcock model may in part be incorrect in some details, but it provides a framework on which to organize all of the complex solar activity. Even though the models of the sky and the atom were only partially correct, they serve as organizing terms of guide your thinking. Similarly, also the precise details of the solar magnetic cycle are not yet understood. The Babcock model gives you a general picture of the behavior of the sun's magnetic field. If the sun is truly representative star, you might expect to find similar magnetic cycles on other stars. But stars other than the sun are too distant to observe as anything but tiny points of light, and spots are not directly visible. Some stars, however, vary in brightness over a period of days in a way that reveals they are marked with dark spots and color fade. Other stars have features in their spectra that vary cyclically with period of year, suggesting that they are subject to magnetic cycles much like the sun. At least one other star, Tau Bootes, has been observed to reverse its magnetic field. Once again, the evidence tells you that the sun is a normal star. Any questions or propositions? So, at this time, I think it's enough for our lecture, and I hope you enjoy this lecture. And moreover, I'm looking forward to seeing you next time. Bye.